In this lesson, we will answer the question, what is the effect of the constant a on the graph of g of x equals ax squared? First, we need to understand what a quadratic function is. Any function that can be written in the following form, where a, b, and c are any numbers, and a is not equal to 0, is called a quadratic function. Notice that the highest exponent of the variable x is 2, or the degree of this function is 2. The most basic quadratic function is f of x equals x squared. It's called the parent quadratic function. You'll see why we call it that. To graph the parent function, f of x equals x squared, you make a table of values like the one below, of input and output values of the function. So for example, if I put a -3 into the function that squares its variable, I get out a 9. If I put a -2 in, I get out a 4, -1, a 1, and so on and so forth. So if I want to graph it, if I graph these points, the shape will look like this. This shape is called a parabola. The turning point of the parabola is called its vertex. So the point 0, 0 on the graph is called a vertex. To understand the effect of the constant a on the graph of g of x equals ax squared, in the following example we will graph the function using various values of a. So we're going to take a look at each of these quadratic functions. The graph of the parent function f of x squared, f of x equals x squared, is going to be shown in black. So let's take a look at the first one, g of x equals 2x squared, and let's see what effect this has on the graph of the function. So here are some ordered pairs for my function. Notice if I put in a -2, using order of operations, I get -2 squared, which is +4, and 4 times 2 is +8. Similarly, if I plug in a -1, I get -1 squared times 2. That's 1 times 2, so I get out a 2. If I plot all these points of inputs and outputs from my function, I get the following graph. Notice it's also a parabola, but the fact that we've multiplied the function by 2 changes the graph of the function in a particular way. Notice it sort of gets stretched in the vertical direction. By multiplying by 2, it gets stretched in the vertical direction. And if we take a look, what if our value of a is 1/2? Well, here are some input-output values for the function if a is equal to 1/2. Okay, and here's the graph of this function. Notice now that the graph is vertically shrunken, because this is the parent function in black, where this right here represents the function g of x equals 1/2 x squared. Notice it's a vertically shrunken version of the parent function f of x equals x squared. Okay, suppose we let a now be some number that's less than 0. What effect does this have on the graph? So we're going to look at the following two functions. We're going to see what effect the coefficient has if it's negative, a -2, and if the coefficient is -1/2. Okay. Well, the parent function f of x equals x squared is shown here. Now here are some input-output pairs for my function g of x. Okay. Now if I graph this thing, notice that the parent function gets flipped over the x, or reflected over the x-axis. Not only that, but it's vertically stretched as well. If I look at the function g of x equals -1/2 x squared, okay, and compare that to the parent function, notice once again it's a reflection over the x-axis and vertically shrunk. Okay, next thing we're going to look at is how can we write an equation for a function, a quadratic function, if we're given the graph of the function. Okay, the way we do it is this. A function whose graph is a parabola with a vertex at 0, 0 always has the form f of x equals ax squared. Now, what we basically need to do is figure out what this coefficient a is for the particular function that we're looking at. To write the rule for the function, you can substitute the x and y coordinates of a point on the graph into the equation y equals ax squared and solve for a. So in this example, suppose that we're given this quadratic function and we would like to write the quadratic function's rule based on the graph. Okay? What we're going to do is we're going to use a given point to find the value of a. Okay? So we're looking for a function of the form y equals some number a times x squared. What I do is I substitute the input-output pair in for my variables. So x is our input, okay, which is 2 in this case, and whenever I put a 2 into this quadratic function, I get out a -1. So the following equation must be true about this function. Now all I need to do is solve for my variable a. Notice that I have -1 equals a times 4, since 2 squared is 4, and to solve for a I simply divide both sides by 4. So I get that a has to be equal to -1/4. This gives me the equation for the function being -1/4 x squared. Okay, so in this lesson we learned what the effect of the constant a on the graph of g of x equals ax squared is. Having a coefficient other than 1 for the x squared term either stretches or shrinks the graph of the parent function vertically. If the coefficient is negative, it reflects the graph over the x-axis so that it opens downward, like an arch or a bridge, instead of upward like a cup. The coefficient does not change the vertex, however, so it's still at the origin.